This is Unit 8 Notes Part 4, The Effect of pH on Solubility. Last Friday, I told you that this set of notes was going to be a little bit shorter and not particularly difficult. Really, what it is just a couple of things that we haven't yet talked about for this unit, but none of it is particularly new or particularly hard. I just kind of have to bring them up so that you're aware of those things. The AP test may ask you about the solubility of salts. You know that they're going to ask you about solubility in some capacity because we spend a lot of time with KSP and ice tables and all of that. But sometimes they ask, okay, this salt, is it going to have an increased solubility in an acidic solution or a basic solution, or some variation of will this salt solubility increase or decrease in the presence of X thing? So when you're considering the solubility of acids and bases and different salts, you have to think about the same two things we always think about with solubility, which is Le Chatelier's principle and the common ion effect. All right, so I've put equilibrium ethyl over here in this corner because she's always there, she's always paying attention. Equilibrium is all over this unit. So the way to explain this is really just to kind of look at the equilibrium systems that we're dealing with. So we have a simple problem. Will calcium fluoride be more soluble in a neutral solution, so that's pure water, or in the presence of an acid? All right, so an acid is very general. It doesn't tell you what specific acid. So we're not actually looking at the common ion effect here because we don't know what the acid is. Instead, we're going to pay attention to Le Chatelier's principle. If I add an acid and then try to dissolve this salt, really what we're talking about here is we're adding H3O plus ions. Because the second I add an acid into water, that acid splits up at least a little bit, and it's going to produce H plus ions, which immediately latch onto a water molecule and form that H3O plus. In terms of how that affects Le Chatelier's principle, those H3O plus ions are generally pretty reactive. And if you're trying to dissolve this salt, those H3O pluses might react with some things in this equilibrium system. So that positive charge means that the H3O plus is very likely to react with anything in the equilibrium system that is negatively charged. In this case, are fluorines. So the H3O plus is going to react with those fluorines. What that does is it creates a little bit of hydrofluoric acid and some water. But more importantly, when these two things react, they are forming other substances, meaning that we are decreasing our amount of product in this equilibrium system, and that is Le Chatelier's principle. When I decrease a product, that means that ethyl and my equilibrium system are going to want to regenerate that product. It's going to want to fix what happened. That creates a right shift, meaning that this equilibrium system in the presence of an acid is going to favor the dissolved products, and it is going to increase the solubility. So once again, to sum up, we tried to dissolve calcium fluoride in an acidic solution. The acid part of that solution, the H3O plus, reacted with the products of that equilibrium system, which made product go away. When I decrease product, my equilibrium shifts to the right, forming more products and favoring the dissolved form of CaF2, which increases my solubility. Let's look at this second sample problem. Our second problem says, will the mass of zinc 2 hydroxide increase or decrease if a small amount of soluble potassium hydroxide is added to a saturated solution? Justify your answer using the reaction quotient Q. Okay, so once again, we're going to use the old very trusty method of drawing a picture just so that we're clear on what is happening. So, we have a saturated solution of zinc 2 hydroxide. Zinc 2 hydroxide is a slightly soluble salt. I know that because of the solubility rules. Hydroxides are generally insoluble with a few exceptions. Zinc is not one of them. So we're going to have quite a bit of zinc 2 hydroxide on the bottom in solid state. But we are also going to have some Zn2 plus ions and some OH minus ions floating around in a saturated solution of that salt. The question asks, if you add a small amount of soluble potassium hydroxide, will the mass of that increase or decrease? So let's talk about that. What we're doing is we're introducing some potassium hydroxide into that solution. And what this question wants to figure out is this mass of solid zinc hydroxide, does that increase or decrease as a result of adding potassium hydroxide into this solution? So that's what's going on. We have our solution of zinc 2 hydroxide. We add some potassium hydroxide into it. Do I get more solid or do I not? That's the question. To figure that out, the first thing you want to do is you want to draw out the existing equilibrium system to see how adding potassium hydroxide is going to change it. So right now, we have zinc 2 hydroxide in solid state, and that is in equilibrium with zinc ions floating around and hydroxide ions floating around, right? If I add, KOH, if I add that, KOH is very soluble. It is a strong base, which means the only thing in this equilibrium system that's common is my hydroxide. So really, when I'm adding KOH, I'm adding product to this equilibrium system. This should sound familiar to you because when I add a common ion, I have to pay attention to the common ion effect. And we know that when we add a common ion and we add product, our equilibrium system is going to shift back to the left, favoring the solid form of zinc hydroxide. So we know, based on the addition of that common ion, that I'm going to see an increase in mass of zinc hydroxide because my equilibrium system is going to shift toward it. Now, before I hurriedly write that down as an answer, you have to pay attention to what your problem is asking you to do. Because it says, yes, will the mass increase or will it decrease? But it asks you specifically to justify that answer using the reaction quotient Q. So we can't just say because of the common ion effect this happens. We have to talk about Q as well. So Q is a reaction quotient, and we get a reaction quotient by taking our product concentrations and dividing them by reaction concentrations raised to the power of their coefficients, right? So if I balance that equilibrium system, I have some coefficients to work with. The nice thing, though, is that we don't actually need a value for Q. We just have to think about it theoretically. By adding my common ion, what I have done is I have added product. When I add something to the numerator, Q is increasing. When I get an increase in Q as compared to K, we know that my reaction will shift backwards because as it's moving toward its new equilibrium, it's trying to get back to K. So, as a result of increasing my Q, I move backwards. I left shift. So we have to say that in our explanation. All right? So let's write all of that out very nicely and neatly. Our question asked, will the mass of zinc 2 hydroxide increase or decrease? Well, we figured out that it's going to increase. So let's say that. So our first answer, our claim, the mass of zinc hydroxide will increase when KOH is added. That's what happens. We have to use Q to justify it, so we're going to explain what happens to Q when we add KOH. All right, second sentence. I've brought Q into my explanation. I have explained when I add KOH, I'm adding a product, which increases my value of Q. Third sentence, as a result of the increase in Q, the reaction is oversaturated with hydroxide ions. That means there's too many products there, causing the equilibrium system to shift left, which increases the mass of solid ZnOH2. You can even add a little bit of reasoning here. In fact, I encourage you to do so if you know why. And so we're just going to tack on according to the common ion effect. So once again, I'd like to harp on this for a second. When you answer a question like this, you can't just say the answer. You need to explain yourself if it asks you for justification, and you need to use the correct thing to justify it. So when I wrote this explanation, the problem asked me to justify in terms of Q, so I brought Q into my explanation. All right, that one was kind of long, so let's look at the next section, acidic and basic salts. Some salts have slightly acidic character, some salts have slightly basic character, and some salts are considered to be neutral salts. And the reason behind all of that is because when a salt splits up, the two resulting ions, the cation and the anion, form different equilibrium systems with the water molecules that they interact with. So let's look at an example. Iron 3 chloride, FeCl3, is going to be considered an acidic salt. The reason for that is because this chlorine comes from a strong acid, right? And so the stronger the thing, that means that it can push the acidity or basicity of the solution. So let's look at the equilibrium systems that both of those things form, right? We have our iron, we have our chlorine. The iron 3 plus ions are going to interact with water molecules, and they are going to form FeOH3. Not a lot of it. It's not as if we dump this salt and we suddenly have lots of base around, but it forms a little bit of FeOH3. That thing is a weak base, which will again interact with whatever water happens to be around it and form some more Fe3 plus ions and some hydroxide ions. But because it's a weak base, it's not going to form that much. So a little bit. The chlorine part of that salt, the chloride ions, are going to react with the water molecules that are around them and create HCl. HCl is a strong acid, which, when a strong acid interacts with water, it's going to form some H3O+. And because it's a strong acid, we're going to form more H3O+. Now, when we compare these two equilibrium systems, we have a little bit of hydroxide, but we have way more H3O+. So overall, when you consider those two together, we have an acidic salt because we formed more of these than we did of these. And that's it. Looking down here to our next example, Na2S, that thing is a basic salt because sodium ions come from sodium hydroxide, a strong base. But again, the sulfur ions are going to do something with water too, so let's take a look at it. Our sodium ions interact with water to form NaOH. NaOH is a strong base. So we're going to form a lot, or not a lot, but more of our hydroxide ions. Whereas our sulfur ions here interact with water to form H2S, or hydrosulfuric acid, which is a weak acid. So we're only going to form a little bit of our H3O+. So when you consider both of these things together, we find that Na2S is a basic salt. If you have a salt that contains the conjugates of a strong acid and a strong base, that's when you get a neutral salt. So NaCl, for example, comes from NaOH, a strong base, and also HCl, a strong acid. So we're going to form approximately equivalent amounts of hydroxide and hydronium, meaning that our salt is largely neutral. For your reference, here's a very nice table, the same table we've always looked at, of our strong acids and our strong bases. Let's look at a sample problem. Determine whether the following salts, when mixed with water, will make acidic, basic, or neutral solutions. So we got to look at the different pieces of these salts. KClO4. We split that salt. The base that could produce potassium would be KOH. The acid that can produce ClO4 would be HClO4. That is a strong base and a strong acid. How do I know? Because I checked with the table. Strong acid and strong base means a neutral salt. Next one, iron 3 nitrate. The base that can produce iron is FeOH3. The acid that can produce nitrate is HNO3. So we've got iron 3 hydroxide, which is a weak base, and we've got nitric acid, which is a strong acid. So we're going to be an acidic salt. Next one, calcium fluoride. We've got CaOH2, and we've got HF. This is a strong base. HF is a weak acid. Therefore, we're going to be a basic salt. For the next three, I'd like you to pause the video and try them on your own, but if you're not comfortable with it, you can see me work through them as well. Cesium iodide. We've got cesium hydroxide, which is a strong base, and we've got HI, hydroiodic acid, which is a strong acid. So that guy is going to be a neutral salt because strong and strong neutralize each other. KClO2, we've got KOH, which is a strong base, and then we've got chlorous acid, which is not a strong acid. That is a weak acid. I know because, again, the table. So that's going to be a basic salt overall. For this last one, there is actually a typo. This shouldn't say NaHSO4. This should say Na2SO4, so please make that adjustment. When I divide those two, we've got sodium hydroxide, and we've got SO4, so that's going to be sulfuric acid. That is going to be a strong base with a strong acid, and that is therefore a neutral salt. Last thing I would like to talk about is the solubility of acidic and basic salts, because there's a little piece of information you just got to know and memorize. Acidic salts tend to be more soluble in basic solutions. The reason for that is because the hydroxide ion in the basic solution will react with any acid produced by that acidic salt, and then we're going to end up shifting to the right. Okay? So if I have FeCl3 in a basic solution, what happens is our hydroxide ion that exists in that basic solution is going to end up reacting with any hydronium that acidic salt presents, right? And as soon as we react these two, we get rid of product, which is going to shift our equilibrium forward to favor our dissolved salt. For bases, we have the exact opposite situation. Basic salts tend to be more soluble in acidic solutions. For a similar reason, it's because our H3O plus in our acidic solution that we're trying to dissolve that basic salt in is going to react with any hydroxide produced by that basic salt. So our H3O plus will come in and react here. Again, we're removing product, which means that we're going to shift our equilibrium forward. So you just kind of have to know, if I have an acidic salt, it's going to be more soluble in a basic solution. If I have a basic salt, it's going to be more soluble in an acidic solution. The AP test will rarely ask you for reasoning on that. This tends to be more of a multiple choice question, but just knowing that information is helpful. On Tuesday, when I see you again, I'm happy to answer any questions you might have about this set of notes, and then I'm going to hand you the test review for Unit 8 as well, so we can start working on that together. Please don't hesitate to ask if you have questions.